Hello friends, I am Tanmoy. I welcome you all in my channel Chemistry, the History of Molecules. So today we will discuss about Anti-Markovnikov's addition or Karsh addition. In previous video I have explained about Markovnikov's addition. So that is the first part, this is the second part. So if you haven't seen that video, I suggest you please watch that video faster. After that you come to this video, it will be helpful for complete understanding because it's a you can consider extension of that reaction. Okay. So in this video what we are going to discuss about, first the basic concept, background this. Second, why peroxide? You can say everywhere it is mentioned peroxide. Why this peroxide? What is the need? Second, amount of peroxide and why very low peroxide is sufficient. And finally, we will discuss why HBr. Okay, here also one interesting point, that hydrogen bromide. Why HBr only? Not on the other peroxide, and that explanation will completely be given based on bond energy data. Okay, so let's start. So as you can see, this is the alkene. Fine. This is the alkene and this is the addition product. This is done in presence of peroxide, so that's why it is called the peroxide addition product. Fine. So this reaction is mainly the addition of HBr in an anti-Markovnikov fashion. Since I am studying anti-Markovnikov fashion, the simplest question comes: what is the Markovnikov fashion? Let's take this example and add HBr. No peroxide. Okay, no peroxide. So what will be the product? Negative part of the addendum according to the Markovnikov rule. I have explained in the previous video details. I am repeating just thing that negative part of the addendum will attach to that, because you can consider this as H plus. HBr is a strong acid and Br minus. So negative part of the addendum will attach to that carbon which is poorer in hydrogen. This has 1 hydrogen, this has 2 hydrogen. So negative part will attach here. So according to the rule, the product is this. So if I write more clearly, then it should look like there is H and there is Br. So this is, but you can see here little reversal in activity. Question 1. So this is the effect of no peroxide. Okay, fine. Now let's discuss about the effect of peroxide. So before going to the details about the effect of peroxide, let's learn what is peroxide. Okay, actually here peroxide means organic peroxide. What do I mean by organic peroxide? Organic peroxide means organic peroxide. Organic peroxide means, for example, you can take dibenzoyl peroxide. What does it mean? This is the dibenzoyl peroxide. Okay, dibenzoyl peroxide. Why I am saying benzoyl? Because this is a benzoyl group. And what happens? It breaks and produces 2 radicals. I'll explain slowly about the mechanism. It generates radicals. Okay. Other peroxide, one is benzoyl peroxide. You can use, apart from that, another thing could be used like EIBN. You know, it's a very famous reagent. Diazo isobutyronitride. Fine, nitrile, not nitrite. So EIBN, and target is the production of radical. This is the target. So this is that. Another, for this target, we are actually producing here the peroxide. Then why we are producing? Sorry, I made mistake. This should not be any carbon. It should directly be attached to this. Okay. So why peroxide is used for radical generation? Because this bond you can see is easy to break by heat or light. Okay, mainly if you say more specifically UV light. So UV light, in presence of UV light, it breaks. And why breaks? Because their bond energy is around 45 to 50 kilocalorie per mole. So what does it mean? If you see the CH bond, the energy of CH bond is around, the energy of CH bond is around 100 kilocalorie per mole. So that is C, it is almost half. So it means that if proper condition is applied, it will instantly break to produce the radicals. So now what happens in this case? So ultimately you understood it generate radicals. So how this is generated? That is by, first of all, it breaks homolytic fashion. Homolytic fashion means equally two bond broken, means, and this corresponding electron came for the construction of this bond goes to the individual atoms, and that's why this is called homolytic cleavage. And it produces, actually keep it in mind, homolytic cleavage of a covalent bond always produces radical, because here one, and this is called fish hook halo. This is the convention to indicate the breakage, means movement of single electron. Okay, so what does it proves? Let's let pH CO minus. This is two amount this produces, and we know radicals are 7 electron species, so electron deficient. So if something is electron deficient, it is unstable. Consequently, what happens? It undergo further reaction. One electron from here and it takes another electron, resulting in this. So ultimately what it produces? It produces from 2 to pH radical. What does it mean? Radical is here, means this orbital, and keep it in mind, this is not in conjugation with the benzene ring. This is in sp2 hybridized orbital. So this carbon is right now electron deficient. Okay, and it's a 7 electron species, this carbon is. So it needs electron, and in this way reaction start. So this process belongs to the initiation of the reaction. Okay, so we have discussed about the basic concept and initiation of the reaction, that is radical formation. So now we have in our hand, that is radical. Now another question, why very low amount of peroxide we use? That question we will discuss now. So this pH radical is going to first react with the HBr. Why? Because HBr, this bond is polar, sufficiently polar. This is delta plus, this is delta minus, and this has a reactivity. And why HBr specifically, I will explain at the end of this video. So this is one electron movement, from this bond one electron, it will come. So what will be the product? It will produce PHH, this is benzene, plus Br dot. So this Br dot is the actual reaction species. So here the initiation step finished. Till now what we have discussed, initiation step. So now this HBS, so in presence of peroxide, what it produces? It produces this Br dot. Okay, so sorry. So this Br dot now reacts with alkene. Why it reacts with alkene? Because alkene is made of a loosely bound pi cloud. Pi, because you know that alkene is a CC double bond. Okay, how it formed? It formed by the parallel overlap of two p orbital. Okay, this is a p orbital. Let's say it's pz. Let's say it's pz. It produces this. Z is the this direction. And this is because for symmetry you can provide, instead of that you can give plus minus that also. No. Fine. So this is electron deficient. Because 7 electron species, electron deficient. It is electron rich and the electron is loosely bound. Consequently, what is going to happen? That this bromide will take electron from a place where it is loosely bound. So this is the first concept. Okay. Okay. So it will react with this. So what it will produce? So let's consider one will come here, this will, and ultimately it will produce. So in this way the product is CH3. This is the H along with the radical, another thing here Br. So why I am writing this? You may argue that no, it will not be produced. Instead of that, it will result in the production of another one. See, what is that? CH3. This is the Br. This is the H. Radical is here. Now, if you say about stability of radical, both are unstable. Radicals are unstable species. Radicals are unstable species. Okay. So now we have to compare relative. So always keep it in mind. Majority of cases I found or I have heard that this is a stable radical. This reaction happens through this because this is a stable radical. No, radicals are not stable. Radicals are not stable. Actually, they are relatively stable. Okay, this is relatively stable. Why? Because you can see here that this radical has 2 hyperconjugation. Sorry, here 2, here 3. This is 5 hyperconjugation possible. Here 5 hyperconjugation possible. Whereas if you compare only 1 hyperconjugation, let's write as a H. So since the stability of this radical less, it is expected that the this radical will not be prepared because the corresponding energy of activation to prepare this radical is higher, and we know that a particular reaction will follow that track which is associated with relatively lesser amount of energy of activation. Fine. So we understood that this will not be followed. This chance is over. Okay. So now the question is, what is the next? Actually, whatever right now we are discussing, this is the propagation. So preparation of bromine radical is done, so initiation is finished. Okay. So this radical is prepared. Now what is going to do? See, a radical this is produced, so it can do few things. For example, it can react with another molecule of this propene. Okay. So what will be the product? So, sorry. It can, okay, there is a chance it can react. Another thing, it can react with HBr. Advantage of HBr is that if it reacts with HBr, ultimately what it will do means this, like previous step, peroxide phenyl radical plus HBr. Similarly, so if it reacts, what it will produce? It will produce CH3, this and Br plus, sorry, H plus Br. Why? Because this H is this one. Understood? So this, so Br is this. So sometime it happens. Just now, let me tell you that I forgot that what will be the product. Then how I found out? I found out because product is this. There should be one hydrogen. Addition of bromine will be there. I know according to this rule. I have added, but here hydrogen needed. So hydrogen will must. So sometime if you forget, you can utilize some common sense, or in local language you can say it's a jugaad. So you can try this jugaad, and in this way you can end up this. So this is the propagation step is over. So ultimately this is the product. Now in every radical reaction there is a case, that is termination. Okay. So I will go, before that one question, why very less amount of peroxide is sufficient? Actually if you see, around 0.01 mole compared to 1 mole, this peroxide is needed. Very less amount. Why? Because in presence of heat, this peroxide generates radical. Fine. this peroxide generates this. Actually, if we take benzoyl peroxide, it generates this phenyl radical. It's okay. What happens? This phenyl radical generates Br radical, and through this mechanism, this Br radical is auto-generated. During the progress of this reaction. So you got understood, and since it's a 7 electron species, electron deficient, so it will continue the chain similar way. That's why very less amount of peroxide is enough. Okay. So now the last step of this reaction, that is the termination. So how termination could be possible? Okay. So in order to understand, you can think something. For example, there is one radical. So similar like another radical. This. They can combine to produce what? This is the methyl. This is, and here also one methyl, Br, and this is Br. One chance. 2 molecule of Br. Means, what do I say? It can react with another Br in this way and produce Br2. This. So, in this way, the reaction could be terminated. But generally, we don't focus on termination. But keep one thing in mind. Why this termination step is important? Because termination produces impurity. Why I am saying it's impurity? Impurity products. Because our target is this, and we are getting majority of this. So there will be some minor product, and that minor product is considered as impurity. And for example, it is 97%. We will say that okay, complete conversion happened. But 3% of this. Why this is important? Because this helps us to understand. This helps us to understand the basic insights that what byproduct it is, because we have used peroxide as 0.01 mole%. So if we use this much amount of less, so expected that production of such product will be very less, and that will help us to understand the mechanism. Now we will discuss about why HBr, because in case of peroxide, because if you see Markovnikov's addition, in that case you can use HCl, HBr or HI. 3 possible you can use. But in case of this Anti-Markovnikov case, only HBr. Why? The answer is based on this energetically reaction is possible, because entropically all are same energetically, and I will explain now how energetically this is possible. Okay, let's continue the last part of this lecture, that is why HBr, explanation based on bond energy. Now as you can see, the CC double bond energy is 145 kilocalorie per mole. Compared to that, what produced here, one CF bond, okay, and here double bond is broken and produced one single bond, means this one and this one. So this CC single bond energy 83 and CF bond energy 107. All the calculation are approximate to give you a understanding. Never argue with anyone that this is the data, because you can see I haven't put any substitution. Okay, so that indicates a very rough calculation for your understanding. Okay, and so ultimately delta H of the process, delta H means energy, means actually this is the delta H, these are energy released and it is negative. So how much energy released here? This is minus, it should be minus actually, okay, because energy is released. So calculation is, how this is calculated? Minus 190 plus this, because this much amount of energy we have given, and ultimately this much amount of release, and released energy is considered as negative. That's why 145. Okay, so ultimately product is minus 45 kilocalorie per mole. So this indicates that the first step is highly stabilized. Okay, highly stabilized means exothermic process. Now in this condition, one thing need to be remembered, I have written F dot and I have provided any energy, because in previous discussion I have told that this radicals are produced from a very low energy species that is peroxide, which energy is around 45 to 50. So that's an in UV radiation that produces radical. So that's why we are not considering. Okay, so don't consider that pattern. Another thing, reaction is a chain reaction. So we don't need to consider the production of this because throughout the chain it will produce. And another thing I have to mention, there are another type of peroxide also, ROOR. Okay, it's a peroxy-ether linkage, you can say. They can also break and produce RO dot twice, and that RO dot actually reacts with this HX to produce this ROH and X dot. So this is relatively, actually this is something different. I thought previously I missed it. So let's give you the thing. Okay, fine. So first step is energetically highly favorable. Okay. So we have observed that the first step is energetically highly favorable. Now the second step we have to focus. So first step is highly favorable energetically highly favorable. We produced a CC bond which energy released in 99. So in this case 99 is octet plus we have given 134. So what is it? Is positive. So delta H is positive. So this reaction is this step is endothermic. Means we have to provide energy in order to achieve this step. So this step is unfavorable. Okay, so that's why this step will not occur, and that is the reason why this HF don't show reactivity for this anti-Markovnikov process. Now, one thing may come in your mind. What? That overall if you consider the process, that is exothermic. But in individual two important steps, one is exothermic, one is endothermic. And overall if you calculate, that is exothermic. But why reaction is not happening? The question is, in order to the completion of this reaction, two step for happening is essential. Otherwise, this step will happen, but that will not happen. So reaction will not ultimately occur. Okay, fine. So this same thing is utilized in case of chlorogel. So this is for fluoro. This is for chloro. Okay. So this is same 145. Similar calculation I am not going to explain. So first step of this process is endothermic. So actually this is highly favorable. We can say this is just favorable. It is not that much high like the previous. Why? Because here CCl bond formation is not that much strong compared to CF. Why? Because it's a 2p second row element. This is also a 2p second row element. Second, and here 2 versus 3. So slight lesser extent of orbital overlap. That is why energy is relatively less. Second, similar thing observed in case of bond energy of this. So the first step we have discussed. Second step similarly less, because this is 102 kilocalorie per mole we need to provide to break the bond, whereas the CF was 134 because the similar thing, extent of overlap because of proper matching. This is second, this is 1, and this is 1, this is 3, so relatively lesser overlap. And in this case you can see CC bond energy, this is a CH 99. So ultimately this delta G is slightly positive, okay, kilocalorie per mole. Slightly positive. So first step is slightly favorable, second is slightly unfavorable. We should write the word slightly unfavorable. That is the reason why this reaction, this peroxide effect in case of HCl addition is not commonly observed because it's slightly unfavorable, but in case of special condition, very few example it is observed. So don't consider that only BR, and means don't be conclusive that only HBr. Yes, it is true. For example, 99% cases HBr shows, but there are also 5% cases where HBr does means HCl also shows the similar type of phenomena. Okay. Now we have discussed about this HCl. Now question is, what is the HBr? Actually, if you look closely, the HBr in case of both steps are slightly favorable, and that is the reason why HBr shows this effect. And second, the bond energy part of ClF is higher because of overlap, but in case of Br, all are in a moderate value. Okay, what do I mean by moderate value? See, the first step is -6, slightly favorable. And if you may ask that, sir, what is the scale? That, okay, first 1 to 10, slightly favorable, 10 to 20, moderately, 20 to, it is not that, it is just based on my opinion. I am not saying that there is a scale and I am following that scale. It is not like that. So, this is favorable. Second step, see the bond energy of HBr because of the pore overlap, 87, and this is 99. So, second step is also significantly, see, both, this is also favorable, -6, this is also favorable, and that is the reason, that's why this HBr addition shows, HBr addition is favorable overall. So, the conclusion is that HBr addition because of both steps energetically favorable, this HBr addition is possible. But as I say, never argue because substrate to substrate reactivity changes, energy changes, it is a common understanding. Okay. Now let's discuss the last one, that is the iodide one. See, the first step of iodide, this Ci bond formation is energetically unfavorable. Delta H is positive. Why? Because this Ci bond is not that much stable enough that this first step is energetically possible. Why? Because you can see it's a 2 and it is a 5. Because fluorine is 2, chlorine is 3, bromine is 4, iodine is 5. And another thing, it is true that this Hi bond is very weak, only 71. So second step is highly favorable. Delta H minus 20. But because of the first steps is not happens, that's why this. And second, for example, in presence of this Hi and peroxide, you produce this ROH plus iodine. Fine, it will happen. But there is a chance that, another chance is that this II recombines, means this, and it forms iodine. So that is another problem of this process. Okay. So that is the overall explanation why HBr addition in presence of peroxide happens, other don't happens. I believe you have understood. So what you have learned today about Anti-Markovnikov's rule, effect of peroxide, what type of peroxide is used, how this peroxide produces radical, why this reaction is chain reaction, which means that why less amount of peroxide is adequate to carry out this process, and finally energy calculation for this HBr addition selectivity means or preference, you can say. This is we have learned. So if you like my teaching, please subscribe my channel Chemistry the Mystery of Molecule and share this video among your friends so that many people could be benefited from my effort. And finally, please press the bell icon to get the notification of every single video I upload. I always try to make videos related to basic chemistry which will improve your understanding. So learn, practice, I guess you will definitely achieve success. All the best. God bless you. See you in my next video.